Okay, let's unpack this. Have you ever felt like you're just, I don't know, smashing your head against a wall trying to get something to understand? Not like a person, but maybe a really smart system, a cutting-edge AI. And it just can't seem to grasp a seemingly simple three-way interaction. Well, it turns out our super brilliant transformer models, the engines behind so much modern AI, they actually hit those exact same walls. For all the amazing stuff they do, there are certain kinds of problems where they just stumble, fundamentally. It's kind of wild. In fact, you could almost rap about it, right? Like if you were a slightly exasperated researcher, maybe late at night, you might think. You prove transformers hit walls on tasks that need three-way reasoning. Match three, function chains, relation links. One-layer softmax can't crack them formally. You craft a new lower bound method, split VC dimension, no precision tricks, it shows why. Standard attention's blind to triplet interactions, stuck in pairs. You build Strassen attention, named for the fast matrix hack. It sees triples, but runs in subcubic time. Smoother than third order, leaner than its kin. You test it on every task. It outperforms standard, matches third order's accuracy, but trains faster, scales better, uses less GPU firepower. You design a quotient task, triangular and standard fumble. Strassen nails it cleanly, proving it's not just another tweak. You realize it's not just a better attention. It's a key to unlock compositional reasoning. In Transformers, without the bloat, they say, but why does it matter? You show it solves what others can't, with math to back it up and speed to scale it out. You didn't just fix an attention bug, you built a bridge between transformer limits and the reasoning they need to reach.
Huh. Well, that's certainly one way to summarize the journey. What's really fascinating, and what that playful summary actually hits on, is a really deep challenge in AI. How do we get these incredibly powerful models to think in more complex ways, more compositionally? For quite a while now, we've seen transformers struggle with tasks where you need to put, say, three or more pieces of information together at the same time. It's not just about pairs. So this deep dive, it's all about understanding why. Why that limitation? What's the formal reason? And then, yeah, exploring this really elegant solution that opens up some genuinely new possibilities. We're going to unpack the, let's say, formal limits of the standard transformer architecture and then introduce you to this novel mechanism, Strassen attention, that gets around them. And it's all based on some pretty clever math.
Okay, let's start with the why then. You mentioned transformers hitting walls on three-way reasoning. What does that actually look like for us, when we're using AI, maybe without even realizing this is happening under the hood?
Right. Well, connecting it to the bigger picture, it means that while transformers are amazing at lots of things, language, translation, you name it, they kind of falter on problems where they need to reason about how three or even more distinct bits of info interact simultaneously. Think of it this way. Standard attention, the core mechanism in most transformers, it mostly focuses on relationships between pairs of things, like word A relates to word B.
Okay, pairs. A to B. Got it.
Exactly. It's really good at that. But a lot of real-world problems, maybe understanding a complex chain of events or finding subtle patterns in data, they demand understanding triplets, A, B, and C all interacting together. Standard attention in a single layer just isn't built to see that. It has this kind of fundamental blindness to those triplet interactions.
So it's not enough to know A relates to B and B relates to C kind of separately. The AI needs to grasp the whole ABC connection all at once.
Precisely. It needs to see the unified interaction.
That sounds tricky.
Yeah.
So what specific tasks really highlight this? Where do current transformers just fall down?
Yeah, the research points to a few really clear examples. One they call match three. Imagine you have a list of numbers. The task is to find three numbers in that list that add up to some target value, maybe modulo m. It specifically forces the model to look at triples of positions.
Not just pairs adding up. Got it.
Exactly. Then there's function composition, like understanding hgx. You take x, you apply function g, then you apply function h to that result. Standard models, they kind of struggle to see that whole chain, hgx, as a single combined operation. They miss the essential three-way link.
Okay. Like seeing the steps, but not the whole dance.
Kind of, yeah. And a third one is binary relation composition. Think about relationships, like maybe person A co-authored a paper with person B. Now, if you want to find an indirect link, like does person A have a common co-author with person C, that requires finding that intermediate person, B. So you need to reason about A, B, and C together. Standard attention, again, struggles to reliably piece together those multiple hops in one go within a single layer.
Okay, those examples make sense. And you mentioned this, split VC dimension. That sounds pretty heavy on the math side. How does that actually prove the limitation? It's not just that they're hard tasks, right?
Right, that's a crucial point. Is it just hard, or is it impossible in principle for the standard mechanism? That's where split VC dimension comes in. It provides a rigorous mathematical proof, what we call a lower bound, demonstrating that a standard single-layer transformer cannot solve these kinds of triple interaction tasks. And here's the really important bit. Unlike some older ways of looking at this, the split BC method shows this limitation holds even if you assume infinite precision.
Infinite precision, so it's not about tiny calculation errors or anything like that?
Exactly. It's not a numerical issue. It's a fundamental theoretical blindness. The math proves that the standard attention mechanism itself is inherently stuck in pairs. It just doesn't have the expressive power, the vocabulary, let's say, to describe these three-way relationships within one layer. It's a core limitation of the design.
Wow. Okay. So standard attention is fundamentally blind to triplets. We've got the map to prove it. What's the fix? Which brings us to Strassen attention, named after that fast matrix hack, apparently. That sounds like the kind of surprising connection we love digging into.
It really is a clever piece of work. So Strassen attention directly tackles this blindness. Now, other approaches exist, like something called third-order attention, which also tries to capture these triple interactions. But the problem is they often come with a huge computational cost, typically cubic running time, O and 3.
Meaning if the input sequence gets longer, the calculation time just explodes.
Right. Exactly. It becomes incredibly slow and needs tons of memory, just not practical for many real-world uses, especially with long sequences like in detailed documents or genomic data. Strassen attention gets around this. It rethinks how you calculate these interactions. Instead of trying to directly compute complex products involving all three input vectors, it cleverly uses pairwise dot products, things the model is already good at computing, and then combines those pairwise results in a very specific mathematical way to capture the three-way relationship.
Okay, so it still sees triples, like you said, in the wrap, but using pairwise calculations somehow makes it faster. How does that get us to subcubic and make it leaner?
Well, what's really neat is that this specific mathematical structure means the whole Strassen attention mechanism can be implemented using matrix multiplications. And thanks to algorithms like the one Volker Strassen himself developed back in the 60s.
The original fast matrix hack.
That's the one. Thanks to algorithms like that, we know that multiplying matrices can actually be done faster than the naive cubic time. It's subcubic. The complexity is something like on omega d, where omega is this exponent that's less than 3. Currently, it's around 2.372, I believe.
Whoa, okay, so significantly better than 3.
Definitely. Especially as n, the sequence length, gets large. This makes Strassen attention much more scalable. It avoids that computational bloat you often get when you try to add more complex reasoning power. It's a key innovation, getting that crucial three-way understanding without the crippling cost.
That is genuinely huge. A theoretical fix that's actually practical and efficient.
Yeah.
But, okay, theory is one thing. Does it actually work when you test it? How does it stack up?
Right. The empirical validation is critical, and the research provides a lot of it. They did systematic comparisons. Strassen attention versus standard attention versus that third-order attention we mentioned, and also versus something called triangular attention.
Hold on. Triangular attention. We've hit standard, third order. What's triangular? And why compare against that too?
Good catch. So triangular attention is another variant people have explored. It's kind of designed to capture relationships that form a specific structure, like a triangle, in the input. Think about tasks with a sequence, like parsing sentences maybe, where one thing depends on two previous things in a specific order. It's more structured than standard attention. But it's still fundamentally different from how Strassen attention captures general three-way interactions, any three items. So they included it in the comparison to show that even this more structured approach still couldn't handle the general triplet reasoning tasks that Strassen was built for. It helps isolate Strassen's unique contribution.
Okay, got it. A thorough comparison. So what did the scoreboard look like? Did Strassen live up to the hype? Did it really outperform standard and match third-order accuracy?
Yes, pretty much exactly as hoped. The results were really quite compelling. First, Strassen attention consistently and significantly outperforms standard attention on all those tough tasks. Function composition, match 3, binary relation composition, and this other one, the quotient binary relation composition.
We'll get back to that quotient one. But okay, better than standard. How about against the other complex one, third order?
There, it either matched or even slightly outperformed the accuracy of third-order attention on tasks like function composition and match 3. So you're getting top-tier accuracy, but, and this is the kicker, Strassen attention was consistently way more efficient. Lower training times, less computational resource needed compared to third order.
Ah, so same or better accuracy, but faster and cheaper to run.
Exactly. It trained faster, scaled better. In some tests, its speed was even getting close to standard attention, which is remarkable given the extra reasoning power. And it was always much faster than third order if you measured, say, epochs per minute. So you get that higher order reasoning without the usual massive performance hit. That's the practical win.
That really is the sweet spot, accurate and fast. Okay, now about that quotient task you mentioned where you said triangular and standard fumble. What made that task the ultimate test?
Right, the quotient binary relation composition task. This was specifically designed to be extra tricky, to really push the boundaries and see if Strassen could do something none of the others could. It builds on the relation composition idea like finding common co-authors, but it adds a twist. It introduces a coloring function. Imagine each person also has a color, maybe representing their university. The task is to find a common link, B, between A and C, but with the condition that A, B, and C must all have the same color. A and D, A, and C must be different entities from B.
Whoa, okay, so like finding common co-authors, B for A and C, where A, B, and C are all from the same university, but making sure B isn't just A or C themselves.
Exactly, that kind of complex constraint. It forces the model to track identity, relationships, and properties, the color, simultaneously across the triplet. It's a much harder compositional challenge. And the results? Strassen attention nailed it. Cleanly got high accuracy, standard attention, and triangular attention. They effectively failed. Couldn't solve it with impractical model sizes or training times.
So that really proves it. Strassen isn't just a slightly better version of the others. It has genuinely unique reasoning abilities.
Precisely. It formally demonstrates that Strassen attention offers these unique compositional reasoning skills that the other mechanisms just lack. It's not just a minor tweak. It's a different class of computation.
Fascinating stuff. So let's zoom out. What does this all mean for everything? You said earlier, it's not just a better attention. It's a key to unlock compositional reasoning in transformers without the bloat. That sounds pretty foundational.
It really is, potentially. The big question is always, why should you care about this research? And the answer here points towards building AI that's capable of more sophisticated, more human-like reasoning. Compositionality, the ability to combine known pieces in new ways, is absolutely fundamental to what we call systematic generalization. That's how we learn and apply knowledge flexibly, not just memorizing specific examples. By tackling this core limitation of standard transformers with something like Strassen attention, we're essentially building a bridge from where current models struggle towards the more advanced reasoning they need to tackle really complex, real-world problems. It's about enabling AI to understand the intricate connections between things, not just surface-level patterns or pairs.
So we're talking about moving towards AI that can genuinely connect the dots more intelligently, more efficiently, not just on these maybe toy research tasks, but potentially for really complex stuff, like understanding dense legal contracts or figuring out how proteins fold, or maybe even helping with tricky medical diagnoses.
Exactly. Those are precisely the kinds of downstream applications you could envision. The paper itself suggests some exciting next steps. Obviously, moving beyond these foundational tasks, which are crucial for proving the concept rigorously, the next stage is testing Strassen attention on large, real-world benchmarks. Maybe applying it within masked language models to see if it improves understanding of complex context, or using it in knowledge graph reasoning, where connecting multiple facts is key. And yes, things like protein structure prediction, where understanding these multi-way interactions between amino acids is critical. That's a huge area. There's also this interesting side hypothesis. They mentioned that Strassen attention might lead to a smoother loss landscape during training.
Smoother loss landscape, meaning training might be easier, more stable.
Potentially, yes, which would be another big practical win, especially for very large models. So overall, this research provides a really strong theoretical foundation plus practical efficiency for building AI that can reason more deeply. It's about upgrading the fundamental building blocks.
It really feels like moving from basic arithmetic to algebra, in a way, giving the AI more powerful tools to work with.
That's not a bad analogy, actually.
Okay, so to wrap this up then, if you wanted to leave us, the listeners, with one final provocative thought from this whole deep dive into Strassen attention, what would it be?
A provocative thought. I guess it would be this. What if the real path to unlocking truly general, flexible intelligence in AI the kind that can adapt and reason in new situations, isn't just about throwing more data and bigger models at the problem. What if it's more about fundamentally upgrading the mechanisms themselves, like attention, making them inherently better at grasping these complex multi-way relationships right from the start? Paving the way for AI that learns to genuinely reason compositionally, not just mimic patterns it's seen. Just think about the sheer number of problems in science and engineering and understanding our world that are basically waiting for an AI that can truly understand how 3 or 4 or more different factors interact simultaneously. Moving beyond just pairs, what new discoveries might that unlock?